talking about. So the first one is calculate alpha and Rm from the below experimental plot. So the given that I write on the right hand side in the purple colors, which the equation already gave us. So we can easily copy the equation, which is this part. We need to obtain Rm, so we just rearrange it and plug in the numbers, same as Kp. But when you look at the graph, you need to look at it carefully because the slope is Kp over 2. So we need to move 2 to the other side to obtain the Kp. And also the green letter that I write, don't forget that kilo is 10 to the power 3. So you can obtain the correct answers. And the second part, the difference between the first part and the second part is the second part, it gave us area and volume to 5 times, basically T. So we obtain the Rm and alpha from the first part to calculate in the second part. So we calculate Kp by plugging the we need to calculate new Kp and B because we have been giving area. At the first question, they just want us to calculate, but in the second equation, they put more condition, so we need to calculate the new Kp and the new B. And in the end, we combine the number together to plug in other T equation. For the next part, Mickey will be the one who explain about the exercise.
Okay. Okay, can you guys see me? Hello?
Yes.
Okay, so let me recap a bit from what Mr. Tirat said. Okay, for constant rate filtration, the pressure drop increases as the cake thickness increases and as the collected volume of filtrate increases. And how does this actually happen? If you go back to the slide where they give about cake thickness over here, you can see that the cake thickness is directly proportional to the slurry concentration. Hence, when we look back at the equation over here, you can see that delta P is also directly proportional to the slurry concentration, which explains why pressure drop increases as the cake thickness increases. Okay, and for the exercise here. Okay, so the exercise says that filtration of some slurry in water at 20 degrees Celsius was done at a constant filtration rate of 3 liters per day. The filter area was 0.04 meters square and slurry concentration was 20 kilogram per meter cube. The experimental data of filtration were collected and presented plot below. So if you look at the question, our filter area is given, the constant filtration rate is given, and the slurry concentration rate is given. But what is missing is the viscosity. If you look back in this question, they give us the viscosity here. Okay, but for this question, they don't give. So how do we actually find that? We find that by searching for the dynamic viscosity. Oh shit. Sorry. There was some problem. Sorry, there was a problem. Can you guys see my screen now?
Yes, I can see now.
Can you guys see my screen now? Can you see now? I think there's some error.
Not right now. Not right now.
So now you can see my screen, yes?
No. We could see before, but not now.
Can somebody share the screen, please? Titira, can you do it? Sorry. Okay, actually, let me try and just come back again. I'm sorry. So sorry for this.
Yeah, take your time.
Okay. Can you see the screen now?
Yes, now. Yes.
Hello?
Yes, I can see it now.
Okay. So since we were not given mu, we can search it up from the internet. Okay, and then we find out that by looking at the units over here, we can change it to Pascal times second. Hence, this concludes that we can use dynamic viscosity to calculate the Rm and the alpha that is asked in the question. And then we are given the slope here. So what we do is, if you look back at the question, and if you look at the lecture note, slope here, over here, represents kV here. Here, the kV. So what I did was equate both sides. Okay, we are given kV value. And the formula of kV also, we have it already. So what we need to do is, we just substitute the values of mu, Cs, a square, dV over dt is given, and we equate equals to 50 over here. Okay, but then for the constraint filtration rate, which is dV by dt, it's given as liters per day. So what I do was, I converted into the SI unit, so that we can cancel it out and get the proper unit here. So I cancel it out, and then I get the value of mu alpha, which is over here. I do the same for the y-intercept. Okay, and then after that, I rearrange the equation and get this. And don't forget to change from kPa to PA, because the unit of viscosity is Pascal times second. And now the next question asks, after the constant filtration rate above, the filtration is then operated at constant pressure drop of 120 kPa. How long does it take to filter 2000 liters of filtrate? So in this question 2, we are given delta P and we are given V. Okay. So what I did was, it says constant pressure drop. So what I did was, I found Kp. And we already have the values of mu, alpha, Cs from the previous example. And we also given pressure drop. And now we can find Kp. Okay. The same thing I repeat, I do it for B also, to find the B. As what we want is the time. And the time from the slide, it is time equals to Kp over 2 times V square plus Bv over here. So I found Kp, I found B, we are given V already. So I substitute all the values over here and I get the answer. And yes, that concludes the presentation. So do you have any questions?
No questions at all?
Are there any questions? I mean, you can ask, like, how do I get this from this? Anyone?
Oh, well, okay then. Yeah, thank you you for your presentation. So yeah, let me recap the whole thing again. Okay, you guys can see my slide, my presentation, right? Can you guys hear me? Everyone can see my slide, right? Okay.
Yes.
Okay. Yeah. So again, like this chapter 10, our last chapter is slightly different. It's different from the previous processes. Like in the previous chapters, we focus on the units with columns, right? Like those units, those processes work with the columns has like equilibrium stages. But this one, yeah, it's kind of a little quite different from the previous process. But the filtration is still considered one of the important separation unit. So that's why we need to talk a bit about it. Okay. So yeah, the filtration, the goal is to separate the solid particles from fluid, whether or not it's liquid or gas, using a filter, and there will be a different, and the driving force usually is a difference in pressure. Okay, like the pressure in front of the filter will be higher than the back of the filter, and like there are many types. Okay, there are many types of filters. Right here, I just mentioned about 3 common types: the K filter, purifying filter, and the closed flow filter. Okay, but actually there are many types of filters. But we're going to focus on today. We're going to focus on like the simple one. It's the K filter. Okay, so this is what it looks like. So basically, at the beginning, at time equal to 0, you're gonna have only a filter. There's no K deposit. Okay, so at the beginning, you only have the filter to filter out the solid, and the flow that going in is called slurry, and the flow that going out is called filtrate. Okay, and as the process continues, as time goes on, there will be more accumulation of the cake. Like the solid particles that got stuck on the filter will get accumulated more and more. So you're gonna get like thicker and thicker cake. Okay, and to do the calculation, if we assume that the flow that passed through the filter behaves as a laminar flow, then you can use Poisson equations. Okay, like this Poisson equation here when you have like laminar flow. Okay, the simplest behavior of flow, the laminar flow, and then for this laminar flow, we can use this equation called Kalman-Coseni, and this one related, like the pressure drop across the cake to the velocity. Okay, and yeah, these are the parameters, the constants that you should be aware of. Like K1, epsilon, S0. So right here, for the simplest case, we can assume that our solid particles are in the shape of sphere, right? If our particles are sphere, then this big phi right here is equal to 1. Okay, but if your particles have different shapes, maybe like oval shapes, ellipsoid shapes, cubic shapes, or some other kind of shapes, then the big phi value is not going to be 1. Okay, you can look up from other literatures to look at the values of phis for different shapes, different types of particles. Okay, and epsilon is the void fraction. Like the higher the void space in the higher the porosity in your cake, the higher the epsilon value. And okay, V is the velocity and A is the filter area. Okay, so like this filter area is the cross sectional area. Okay, cross sectional area perpendicular to the direction of the flow. And we can relate the cake thickness, to V, the volume of collected filtrate, by using this equation. Okay, so basically this equation kind of is kind of related the mass. It's developed based on the mass the mass of the solid accumulated in the cake. Okay, so L times A is the volume of the cake, right? Multiplied by 1 minus epsilon. So it's going to be only the solid part of the cake multiplied by the particle, the density of the particle. Okay, and this will be equal to Stirling concentration Cs times V. Okay, so you have to be careful here. Cs, the Stirling concentration, is defined as the solid per the volume of the filtrate. Okay, not the total volume of the feed. Okay, it's not the same. This Stirling concentration is based on the volume of the filtrate, the liquid that comes out of the filtration system, not the solution that not the feed solution that get into the system. Okay, it's after the process. This volume of filtrate. Also, V here is the volume of collected filtrate, not the total volume of the feed. Okay, so be careful of the definitions here. Okay, so from this equation, you can rearrange it into this equation here, and then you can you can substitute this this relationship back into the Kalman-Cozzeni equations, like this L right here. Okay, goes into this L right here, and then rearrange the equation, and this is what you have. Okay, so it's basically the relationship of the volumetric flow rate to the pressure drop across the cake, and also to this resistance within the cake, the cake resistance to the flow. Okay, this alpha right here is basically the property, it's intrinsic property of the cake. Like the higher of alpha value, the more resistant of the cake to the flow. Okay, this alpha value does not depend on the size of the cake. Okay, this one is just it's a specific property. So this alpha doesn't depend on the size of the cake, but it depends on the type of the material, of the like molecular structure, the microscopic structures of the cake itself, not the size of the cake. Okay, so just be aware of that. And usually this alpha is going to be a constant. Okay, this alpha is going to be constant. But in some cases, alpha is not actually a constant. It depends. It's a function of like the pressure of the cake, like this or like this. Okay, so basically this some cases are like maybe a little bit more complex, complicated cases when alpha is not actually a constant, and it is a function of the pressure drop across the cake, and you can like determine all these S prime, alpha zero prime, and also beta. I think that I'm missing beta here. Like these values, you can only find them from experiments. Okay, you have to do like do experiments and get the data and do some data fitting, find do maybe polynomial regression something to determine these constants. So this constant based on experiments, not any theory. Okay. But for the simplest case, we're just gonna say that alpha is constant. And so this is the relationship between the flow rate to the pressure drop across the cake, right? So by using the same concept, the same analogy, you can also develop an equation for the filter. Okay, so this one right here is gonna be the relationship between the flow rate to the pressure drop across the filter and the resistance within the filter. Okay, so and then overall you can combine both resistance resistances of the cake and the filter together, right? Because like during the process, the flow is gonna experience both resistances. It's gonna experience the resistance from the cake and also the resistance from the filter. So we can combine, this equation and this equation together to derive this overall equation that relates like the flow rate to the total pressure drop across both cake and filter, and is affected by both resistances, the resistance in the cake and the resistance in the filter. Okay, and that's also like fictitious volume of filter right here, VF, which is you can see here, it's basically related to the resistance in the filter. Okay, so we're going to use this equation here for our calculations for the filtration system, and also this is something extra. If like in some cases we are interested in the values of wet cake and dry cake. Okay, dry cake means just when we look at just the solid accumulation of the cake, but usually the cake has some porosity, right? It has some voids, so usually it takes up, it absorbs, it holds some of the liquid. Okay, so if you have the cake that also holds some of the liquid, it's gonna be wet cake. But if you remove all the liquid from the cake, it's gonna be dry cake. Okay, so you can use these equations. Basically these equations just like different versions for your calculations. You can use this to find the amount of wet cake, the amount of dry cake, the ratio of wet cake to dry cake, or many other things. Okay, so right here there's also the value CF, which is the solid per volume of liquid phase. Okay, so CF is not the same as CS. Okay, CS is solid per volume of filtrate that we collect, but CF is the weight of solid per volume of liquid phase. Okay, it's like the inlet feed at the beginning before going into the filtration system. And also we have VF, the volume of liquid feed, which is different from V. V is the volume of collected filtrate, but VF is the volume of liquid feed. Okay, and and this we also have wet cake, MF. MC is the dry cake, and rho here is the density of filtrate, of the liquid filtrate. Okay, not including any solid. Okay. Yeah, so you can use like these equations to do calculations however you want. Okay, so so the equations that we develop, that show the relationship between the flow rate to the pressure drop. we can use this equation into two mode of operations. Okay, there are two mode of operations for the filtration. The first mode is to do the constant pressure. Okay, so in this mode, we try to keep our pressure drop constant. Okay, we try to make sure that the pressure drop is constant in the system is constant, but it's gonna change the flow rate. Okay, so so if you look at this equation right here, usually the goal is to determine the properties of the cake, like the alpha value, or maybe the property of the filter, like the RM value. Usually, if you look at this, it's a little bit it's not a linear equation, right? Like you have dV by dt, and some of the terms multiplied together. So you cannot directly use this equation because it's not in a linear form. But to find, but you can flip over, you can inverse the equation before, and get this equation right here. Okay, and then this, you're gonna get the new parameters called Kp and B. Okay, and these are just constants. Okay, and then from this you can do the integration from time equal to 0 at the beginning to time of t, like the end of the process. Okay, and do the integration from when we get filtrate volume equal to 0 and to the final volume of V. Okay, so we do the integration here, and then finally we get this equation. Okay, and then from this you can divide both sides with V, and then you get this equation right here, and you can make a linear plot, do the experiments, measure the volume of the filtrate that we collected over time, and then make a linear plot of T over V versus V. Okay, and you're gonna get some sort of linear line, and the slope and the intercepts of the plot that you make is gonna tell you the values of alpha and RM, the properties of the cake and the filter that we use in the system. Okay, so this is how you analyze the process of constant pressure filtration. Okay, just basically rearrange the equation that we have before into this form right here to determine alpha and RM. Okay, and there's also another mode of operation is going to be constant rate filtration. Okay, so this time we try to keep the volumetric flow rate to be constant, and then here the pressure drop is going to change instead. Okay, so the pressure drop is going to vary during the process, and again, but the goal is the same. We want to find RM and alpha, but at different mode of operations. So from the equation as before, we rearrange it into this form right here. Okay, and then you're gonna get the slope and intercept by plotting the experimental data of pressure drop versus the collected filtrate volume. Okay, so once you get the data, make the linear line, make the linear plot, you're gonna get the slope, and you can use the slope to find Kv and C, and then from Kv and C you can find alpha right here, and use C to find RM. Okay, and as the cake, as you continue the process, right? Like during the working of the process, you're gonna get like thicker and thicker cake, and you're also gonna get like higher and higher pressure drop. Okay, so so that's the idea. Like there are two modes of operation for the filtration. Okay, and this is one of calculation example for this chapter. So in this case, we have a slurry of calcium carbonate. in water. Okay, and the problem says that we try to use constant pressure drop. Okay, so the filtration is gonna operate at a constant pressure drop. So we're going to use this like this equation on this page right here for our example. And some people did some experiment and got this linear relationship between delta p. Sorry, this one. So some people did the experiment and got the this relationship between T over V versus V, right? So and from this we know that the slope is equal to Kp over 2 and the intercept is equal to B, right? From the lecture slide, from the lecture, and we also we know that B is equal to this, so we can rearrange it to find Rm. Okay, so I think that the tricky part is to make sure that all the units are cancel out. Okay, so just like in any engineering problems, you have to be careful of the units. Okay, make sure that all the units, like match with each other, cancel with each other to get the right unit in the end. Yes, so watch out for the units. And then once you get Rm, then you use this relationship to find alpha. Okay, and then this is the value for alpha. So you got the value of Rm, the resistance of the filter, and alpha is the specific resistance within the cake. Okay, and then for the second problem, they say that they want to use the same slurry and use the filter with the same filter cake materials, and also use the same constant pressure. But the difference is that this time they put like many frames, like 20 frames of filter materials. Like before in question 1, they only use one filter, but this time they use 20 filters. So it means that you're gonna have more areas to filter out your process, your feed. Okay. So then then like your area is gonna be like 20 times, like 20 times this area here. Okay, and then so you have to recalculate, find the new value of Kp here, and then you also have to recalculate the value of B. Okay, and finally the question asks for filtration time, right? Like how long it takes. How long does it take to get like the volume of filtrate to be 3.37 cubic meter? So you can use this equation right here to solve for the times, and this is the answer. So it's about 4 minutes. Okay, about 4 or 5 minutes to do the process. Okay, so this is an example for the pressure drop, constant pressure drop filtration. Okay, and then for this exercise, we also given the linear relationship between delta P and V, and it says that they try to use the constant filtration rate of 3 liters per day. Okay, so this one is gonna be constant rate filtration. Okay, and this is how I did. Okay, so this is what I did. Since we know that the slope is equal to kV, right? The slope is equal to kV. Then we can find kV here, and then rearrange the equation to get alpha, and this is what we get. And also we know the relationship. We know that intercept is equal to C, and we know this relationship here. So we can find C and then calculate Rm and got the answer. So now we know the values of alpha, which is the specific resistance of the cake, and we know the value of Rm, which is the resistance of the filter. And then for the second question, so they switch mode of operation. They switch mode of operation from constant rate to constant pressure drop. Okay, they switch mode from constant rate to constant pressure drop, but using the same cake material, the same filter material. Okay, and it asks like how long does it take to filter 2,000 liter of filtrate. Okay, so this time we have to switch equations. Now we have to use the equations for the constant pressure filtration instead. Okay, so in equation 1 we use the equations for constant rate filtration, right? But in second problem, second question, we switch to the equations for the constant pressures. Yeah, and then you just put it on the numbers that are given. Okay. So like because alpha and rm from question 1, you can use it here, and you got the answer for Kp and B. And once you know Kp and B, you can use this equation here to solve for times. And it's a little it's a very long operation. It's like almost a year. So but if that's what it is, then that's what it is. Oh, sorry. I got off a little bit. Okay. So in the end, so in question 1, you guys can hear me, no? So in question 1, we used equations for the constant rate filtration, but in equation 2, we switch to the equations for the constant pressure filtrations. But since we use the same cake and the same filter materials, so we use the values of alpha and rm that we obtained from question 1. We use them in question 2 to calculate the time of filtration. Okay, and this is the answer. So I think like the trickiest part would be the units. Okay, so make sure that you use the right units. Okay, like make sure that all the units are cancel out and everything. I think that's the trickiest part. But the equations themselves, they're not that difficult to use. Okay, so any questions? Yeah, chapter 10 is quite short, not much to be worried about. Okay. Okay, so I don't know if this is what you're waiting for, but let's go back to the exercise of chapter 9. Okay, so last time I think I finished the lecture materials for chapter 9. Okay, last time I finished the materials, the lecture for the chapter 9. So this time I'm going to show you the solutions for the exercises. And I think I got the answers about the same as your friends. But anyway, so for chapter 1, we deal with the liquid. Chapter 9 is the liquid extraction, right? So for chapter 1 is gonna be counter current. It's gonna be counter current extraction. Okay, so you want to extract acetic acid. Extract acetic acid from water into 3-heptanol. Okay, so basically your acetic acid is solute. Okay, acetic acid is your solute. Water is your diluent. And 3-heptanol is going to be your solvent. Okay, I use the graphical technique. Okay, I use the graphical technique to solve, and yeah, I like the equilibrium line is given here. So I have to plot the operating line. Okay, the blue line here, and that's what I did. Okay, you just need to find 2 points and like 2 points here and here. Okay, so from this, yeah, this point right here is x0, y1. Okay, and this point right here is xn y xn yn plus 1. Okay, so once you get 2 points here, then you can draw this operating line. Okay, so I use the mass balance here to find y1 here. Okay, so yeah, so once you draw the lines, you just draw the steps, and then I got the answer to be about 10.5. I think your friends, when they show the solutions, I think they also use like Kremser equation, right? Yeah, like you guys can also use like Kremser equation for this analysis, because Kremser equations is originally used in the stripping and absorption unit, right? But it can also be used here in the liquid extractions, because it also like work in the column has many stages. But the Kremser equations, only give you the result, like the end result. It doesn't give you like the results in the stages in the middle, like in between. So that's a pro and con. Maybe you guys familiar with like using equation to solve the problem, and less familiar with this graphical technique. But the graphical technique, like McAfee here, like can give you some information of the stages in the middle. So maybe sometimes you want to know what's going on in the middle of the column, then the graphical technique give you a better idea than the Kremser technique. Okay. So that's question 1. And then for question 2, okay, for question 2 here, this one is the cross flow. Yeah, it's the 4-stage cross flow system. Okay, it's gonna be a cross flow system. Okay, I'm just gonna show you my result here. So this, when you draw the picture, it's gonna look something like this. Okay, it's gonna look something like this. The trickiest part is this middle feed right here. Like usually you only have one feed, right? One raffinate, like one raffinate feed. But this time you have like the feed that get into the middle of the process, like this one. Okay, so it's gonna make our calculations a little bit more complicated. But anyway, I think your friends use like analytical technique, right? I think they this stage by stage calculations, like do mass balance each stage one at a time. You guys can also do that. I mean that works too. But I also want to show you guys that it can also be done by the graphical technique like this. Okay. So like you start from this point right here. Okay, this point right here, and then you find R over E for stage 1. Like this point, the slope, then you can draw the line, right? And then it's gonna hit the equilibrium line right here. Okay, and then you go down here, like go straight down to this point right here, which is the feed, the composition, the composition that get into the stage 2. Okay, and then you find R over E for stage 2. Okay, so you know the point, you know the slope, then you can draw the line and again hit the equilibrium at this point here, and then you go down here. Okay, but the thing is in this problem you have this middle feed, right? You have the feed that gets into the middle here. So then this is what happens. Okay, it's gonna move the next line a bit to the left. Okay, it's gonna move a bit to the left right here because of the feed. Okay, so yeah, it's gonna to here. So this is so usually if you don't have the feed, it's gonna go. It's usually just gonna continue going. I don't know where it's gonna go, but maybe something like this, and then you do like maybe something like this. Okay, if you don't have the feed, that go into the middle, but because you have the feed, then that's why you get some kind of gap here. Okay, because of the feed, you have a gap here, like it shift the graph a bit to the left. Okay, so that's what happened. So yeah, so in the end, it shift the graph, and from the graph you can find the answer, for this problem, because the problem asks for also like the Raffinated fraction leaving stage 4 and the extract fraction leaving stage 4. Okay, so from the graph is this point right here, and this one is R over E for the third stage, and this is for the fourth stage. Okay, so yeah, you can use the analytical technique, do the mass balance stage by stage to solve the problem, or you can also use like the graphical technique, like what I did here, also to do the analysis. Okay. And finally, the last problem. So the last problem, this one probably maybe one of the most difficult thing to understand in our class is dealing with the partially miscible system. When you have three compounds that are in equilibrium with each other. Okay? So like before, we say that the diluent and the solvent, they don't interact with each other, right? They don't dissolve. They are totally immiscible to each other. But in many cases, you get diluent. You get a mixture of diluent and solvent. Like they mix with each other. Like in this case right here. So we're trying to recover pyridine from water using chlorobenzene. Okay. So our pyridine is our solute. Okay. No, I think A. Just call it A. Pyridine is our solute A, and then water is our diluent. Okay, it's gonna be the diluent, and chlorobenzene is gonna be our solvent. Okay, so in this case, the water and the chlorobenzene, they are partially miscible with each other, and these are in this table right here. They are the equilibrium data of these three compounds. Okay, so from this, you need to be able to draw a triangular diagram. Like the triangular diagram for the three components. Okay, so at this is what I have here. But this one kind of show you like the final look. But okay, so let's say if you look at the table right here. So first, you have to identify which belong to which phase. Okay, like which data set belong to which phase. In this problem is already specified for you that right here, this is the data for the extract phase, okay? And right here, this set of data is for raffinate, okay? So they already kind of separate the data for you, okay? So what you do is, first you start with triangular diagram, right? You have a triangular diagram. So right here is 0, 1, and 1, right? So for the vertical line, this point right here is gonna be just to make sure. Yeah, wave fraction of pyridine. Okay, wave fraction of pyridine. So A. Okay, so 1.0 A here. And is there, and then the diluent is at this end. Okay, D is at this end, and then you have solvent right here. Okay, so at this point, at the top angle, right here you have 100% solute, 100% solute, and at this point, at like the bottom right angle, you're gonna have 100% diluent, and at this point, the 0 point here, you're gonna have 100% solvent. Okay, 100% solvent. So then first I use this set of data like the extract phase. Okay, the extract phase. The extract phase is gonna be on the left side. So if you make a plot, it's gonna look something like this. Okay. So this plot right here, this line right here is for the extract phase. Okay, this one is for the extract phase. Okay, using this set of data here, when you make a plot, it's gonna look something like this. Okay, and then if you use raffinate phase, okay, if you use the data of the raffinate phase, you're gonna get the other line on this side here. Okay, you're gonna get the line on this side here. Okay, so and the whole thing is called solubility envelope. Okay, so on the left side is the extract line, okay? And on the right side is gonna be the raffinate line. Okay, just to make sure. I think that's what it is. Yeah. So okay, so you from this data you got the extract line. From this data you got this raffinate line. Okay, so this is how you read the data from the table. Okay, and then you want to find the tie lines. Okay, the tie lines. What I do is I use this set and this set of data. Okay, because these two they are in equilibrium. Okay, they are in equilibrium. Okay, so like 1.1105 is in equilibrium with 0.0502. Okay, so this one is like extract phase. So extract phase is YA. Okay, this one is YA, and this one is XA. Okay, this one is YA and this one is XA. Okay, and they are in equilibrium with each other. Okay, so I use the information because they are in equilibrium with this. Okay, and this in equilibrium with this. Okay, and this equilibrium with this. Like they are equilibrium with each other. Okay, so from this information, from this information, I can use them to draw the tie lines. Okay, so it's gonna be maybe draw maybe something like this, something like this, something like this. Okay, so for example, I use like three pairs of data, three pairs of equilibrium data to draw three tie lines. Okay, so I use like in this table right here, I have like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So actually I can draw nine tie lines. Okay, using this data from the table, I can draw 9 tie lines on the triangular diagram, but I don't have much space here. I just gonna show you example. So let's say I use three data sets to make 3 tie lines like this. Okay, and then from these tie lines, I can find something called the conjugate line. Okay, so the conjugate line is gonna be something like this. Maybe like this. I like this point and this point. Then from this point I go up, and then from this point I go horizontal to the right, and then I got this point here. Okay, so this is one point I got from this tie line, and next for this tie line, I find another conjugate line, a kind of conjugate point. So it's this one right here. Okay. And then from the next tie lines, I get this point. Okay. So from the 3 tie lines, I got 3 conjugate points, and then I can connect them. And then I can connect them to each other. Okay. So I got something called conjugate line. Okay. So this is my conjugate line. Okay. Conjugate line. Okay, this is called conjugate line. And then once I got this, I can use it to my analysis to find the number of stages later. Okay, and that's what I'm going to show you. Okay, so yeah, for now, this is how I use the information from the table of equilibrium data to find the extract line, the raffinate line, and to find the solubility envelope, and then also use the data to find the tie lines in order to find the conjugate line, which I will be used later. Okay, so from this, let's go back to our problems here. So in this problem, from the table, I got this, like this extract line, and this raffinate. Okay, this is the raffinate. Okay, so on both sides, and then I kind of connect to each other. So this will be my solubility envelope. Okay, so the blue line is what I did to get the solubility, and this is my conjugate line. Okay, the orange line, I got the conjugate line from what I did before. Okay, from the data from the equilibrium data table. Okay, and then the problems give me the information about the field. Okay, and it tells me this point right here. So this is the field. This point right here is my field. It's my field, which is equal to Rn plus 1. Okay, so this is given by the problems. And then next, it also say that my at the solvent, the solvent point right here is a pure solvent. It's pure solvent, so it's at point here. So this point is also given. S is also called E0. Okay, E0 here. And then the problems and also the problems also give us this information here. Okay, like information at the end, like we want YAN to be 0.2 and XA1 to be 0.04. Okay, so 0.04 is right here. Okay, so this point right here is our R1. Okay, this is R1. Like at XA1 is equal to 0.04. So this point right here is our R1. Okay, is the raffinate that leave stage 1. Okay, at so we get the information here R1. Okay, so we know 3 points. Okay, so we know 3 points here, and then we know S, we know Rn plus 1 the field, and then from the plot we know R1, and then En. Okay, En is also given because we know the composition that leave stage N for the extract. Okay, so it say right here that is point 2, so it should be this on this point right here. Okay, point 2. Okay, so we know 4 points. Okay, so we know 4 points. Then we can once we know 4 points, we can draw intersection lines. The intersection lines, right? And I get point M here. Okay, I got point M here. So I know that point M is this one right here. Okay. And then since we know this relationship is from the lecture note. Okay, this equation is from the lecture note. Then I rearrange the equation to solve for E0. Okay, and then I got this the flow rate of solvent required E0. Okay, and then I use like the graphical technique to find the number of stages. So I start from R1 here, and then I have to find the tie line, this green line right here. the way I do it is like from this point, I goes up and then it hit the conjugate line. Okay, this is the conjugate line, right? So it hit this point here. So and then I go to the left. Okay, so and it's gonna hit this point here, and then I draw this tie line. Okay, so from R1, I find this point here, and this point is my E1. Okay, this is my E1. Okay, and then yeah, I forgot to mention. So and then I can draw, you know, like two lines passing these four lines, these 4 points. So the first line, you know, from R1 to E1. Yeah, I draw from R1 to E1, and then from F past the point En, and to get the intersect point here, the delta point. Okay, and then from this, you know, okay, and then once I know R1 and then find E1, right, I can draw this overlapping line, you know, from the delta point to E1 and go to the other side and hit this point here. So this point is R2. Okay, and this point is R2. R2 right here. And then again, I use the conjugate line to find the other side. So this one right here is my E2 actually. Okay. So yeah, this one is my E2. But since E2, what I say? Okay, so this point is E2. Okay, this point is E2. But this E2 is higher than En, right? So it means that our number of stages is slightly lower than 2. Okay, so yeah, I estimate. So this is okay. This is E1, right? This is E1, and this is E2. But our En is right here. Okay, so that's why I say that the number of stages is about 1.7. Okay, so that's why I got 1.7 because En is just below E2. Okay, higher than E1, but but just almost E2. So it's about 1.7. Okay, so this is how I find the number of stages by using this graphical technique. Okay, and also I can wait a second. And okay, and also I use another graphical technique like this one right here. I don't know if you can see it. So for this one, I use Mackett field. I use Mackett field plot in combination with the triangular diagram. Okay, so but for this one, you don't need to use conjugate line. Okay, so this one, no conjugate line needed. Okay, no conjugate line needed. But you need to find the delta here, and the delta you have to find from knowing, you know, En, F, S, and R1 here. Okay, so from this, I use this information like to transfer the information from the triangular plot to the right side. You know, like from this information, I can make this operating line. Okay, this is my operating line here, and this is my equilibrium. Okay, and this orange equilibrium comes from the data of this table. Okay, just like I say here, this is YA, this is XA, right? YA and XA. YA is the composition of solute in the extract. XA is the composition of solute in the raffinate. Okay, so yeah, I got these two set of data here, YA and XA. So I use this YA and XA on this graph right here, on this orange line, and on this one it's just x equal to y. Okay, XA equal to YA. Okay, but this one is the equilibrium between YA and XA. Okay, YA and XA here. So yeah, so then I can draw the steps, and I got right here. So like you need to use the black line when you find the operating line, the blue line, you need to use the black line x equal to y. Okay, like you need to use the black line x equal to y to find the operating line, the blue line. But after that you don't need the line x equal to y anymore. Okay, you only want to draw the steps between the operating line and the equilibrium line, the blue line and the orange line, like this. Okay, and I draw the steps, and I got about 1.8. Okay, about 1.8, which is kind of close to the previous result, 1.7. Okay, so both techniques are quite okay in this problem to use. Any questions? So that's how I solve this problem. You guys still with me?
Yes.
Yeah, this one. Yeah, this one you have to like take times and read and like study it a bit. You know, it's not that complicated once you know what step to do. So, but yeah, it takes time. It takes practice. So hold on a second. Function. Okay. Okay, so yeah, so I suggest you to review how to draw these lines, you know, like how to construct the triangular phase diagram, how to, you know, find how to find the M point, the delta point, how to draw the lines, you know, like so that you can do something like this, okay, to find the number of stages. And actually, there's something that I want to mention. I think in the lecture in chapter 9, yeah, I think it's wrong here. Okay, on this one, it's not en plus 1. Okay. It's just en. Okay, this one right here. I think on page 29. Okay, on this example. Sorry if I make you confused, but it's not en plus 1. There is no en plus 1. Okay, but there is en. Okay, so fix this. any question? So actually that's all the material that I wanna teach you that we want to learn about in for the second half of the separation. But before you guys go, there are a few things that I want to tell you. I want to ask you. So as you know, like you guys already know the time for the final, right? So we plan to have the final on May 21st, okay, from 9 to 12. Okay, on May 21st, 9 to 12. So it's gonna be online exam, and let's see. Hold on a second. What I want to say is that so probably we like on the calendar we have 2 weeks of lecture left. Okay, so like next week and we have next 2 weeks left. But I don't know, like we already cover all the materials. So maybe I'm thinking you guys still want like some kind of review session, I suppose. I don't know. Or like if you have questions, you can like ask me. So what do you guys think? Like we have according to the calendar, so we're gonna have next week lecture April 28th, right? And May 5th. So we have 2 lectures left on April 28th and May 5th. But I'm thinking of not having next week lecture, but maybe we will have the last lecture on May 5th, so that then you guys can ask me questions. Otherwise, I'm just gonna go through all the exercise from every chapter again. What do you guys think? What would be the best for you?
I think as you say, I think it's a best decision.
Okay. Yeah, because yes, as I said, like all the materials that I think you guys should know that we already covered them all. Of course, like you still don't you still need time to review the stuff, right? So maybe, and we have the exam on May 21st. Then maybe the closer the better, or not. So I think so then maybe no class next week. So we're not gonna have class on April 28th, but we're going to